Hi, my name is Susie Feist. I'm a senior in aerospace engineering at Auburn University, and I'm the president of the Auburn University Rocketry Association. We're a student-led organization that focuses on engineering rockets, and we compete in 3 competitions a year. And this is our video for the Argonia Cup Challenge. We manufacture as a team as much of our components in-house as possible, and we're divided into 3 separate teams: our payload team, structures team, and recovery team, each focusing on different components of the rocket.
Hello, my name is Henry Fowler. I'm a junior studying mechanical engineering, and I'm the chief engineer for the Argonia Cup this year. This year, the challenge has led us to make the smallest vehicle in Aura history, which is a 2.2-inch diameter rocket. Our target altitude is about 20,000 feet, and our target score is 77,000 points. This year, we have a lot of new components and systems, and we tested them on the second stage flight earlier in October. This flight was a massive success and tested all of the new components that we needed to test. In February, we're hoping to have a full-scale flight with both the booster and the sustainer. And once that is completed, we'll be ready for the competition. As Susie mentioned earlier, there are 3 sub-teams, and each of them will talk now about their specific role on the team and what they've accomplished.
Hi everyone, I'm Elizabeth Bonema. I'm a senior in aerospace engineering, and I'm the recovery lead for this year's Argonia Cup. Our Argonia Cup vehicle this year is a little bit different from vehicles we've had in the past, especially on the recovery side. Rather than a dual deploy, dual separation recovery system, we're doing a dual deploy, single separation recovery system. This allows us to have less room taken up in the rocket for parachutes by only having one main parachute tube. We still have a main parachute and a drogue parachute, they're just together in the same tube. When the drogue charge separates the vehicle at apogee, the drogue parachute comes out while the main parachute is held tightly in a bundle near the drogue charges. Rather than the main parachute coming out of its own tube at deployment altitude, it's held together inside the vehicle by these. These are cable cutters. A zip tie runs through this center hole, holding the parachute together after drogue deployment. The main parachute stays bundled up until deployment altitude, around 500 or 600 feet. Then a charge inside of here fires, shearing the zip tie and allowing the parachute to unfurl. This single separation cable cutter system is the same in both the sustainer and the booster. Our vehicle this year is also a little bit different on the side of staging. Rather than staging from the sustainer like we typically do, we're staging from the booster. This allows us to hot stage. By hot staging, we retain the booster on the sustainer for a longer duration of time after burnout. This gives us a better coast following booster motor burnout. When we're ready to ignite the sustainer motor, a signal is sent up an EMAG into the top of the motor using an altimeter from the booster. The force from the motor shears shear pins connecting the sustainer and booster tubes together. This hot staging is something new to the club that we've never done before, and we're excited to see how it turns out. Now I'll talk a little bit about the electronics we have inside the vehicle. Going from the bottom up, first we have the booster bay. The booster bay contains 2 featherweight Blue Raven altimeters and 1 featherweight GPS. The power to these is controlled by magnetic switches. The use of magnetic switches prevents us from having to take up room inside the vehicle through physical switches that you would have to turn on from outside. This is our second competition vehicle that we've done using magnetic switches, and I personally really enjoy them so far. The use of the Blue Raven altimeters allows us to control both parachute events and ignition events. That's why we're able to hot stage from the booster with only 1 bay. This is the booster bay coupler. It actually sits in the rocket like this. The parachutes are attached here, the drogue charges are here, all the altimeters and electronics are within this center section, and then this bit attaches to the sustainer. Inside of here, there's a bulkhead with a hole where the wires exit to enter the sustainer motor. Inside the sustainer, there's a similar yet smaller bay. This bay contains 2 featherweight Blue J altimeters and 1 featherweight GPS. The sustainer electronics are simpler as ignition is not needed to be controlled from here. For our parachutes, inside of the booster we have a 3-foot long streamer and a 2.5-foot diameter toroidal parachute. The streamer is deployed at apogee, while the toroidal parachute is deployed at 500 feet above ground. Inside of the sustainer, there is also a 3-foot long streamer and a 3-foot toroidal parachute. The parachute for sustainer is deployed at 600 feet altitude. For our ignition logic, we're using the time altitude lockouts. For these lockouts, the velocity of the vehicle has to be greater than 200 feet per second, Our time since liftoff has to be less than the intended staging time plus 2 seconds. And our altitude has to be greater than 75% of the intended staging altitude. The exact numbers for these parameters will be determined at a later date closer to our first full-scale 2-stage test flight.
Hi, my name is Vaughn Milken. I am a sophomore in aerospace engineering, and I am the Argonia Cup structures lead. For our motors this year, we're using the K805 for a booster motor. It has 1,751 newton-seconds of impulse. And for the sustainer motor, we're using the K270, which has 2,155 newton-seconds of impulse. For each of our motors, we're using the forward retention method, as this proves easier for minimum diameter. Our off-rod velocity is 91.2 feet per second. Our max speed is Mach 1.2. The sustainer apogee is predicted around 23,000 feet, and the booster apogee is predicted around 5,500 feet. For all of our tubes, we use a wet fiberglass layup that we make in-house. Each tube is made with 6 rolls of fiberglass. Our fins and bulkheads are each made with a 2-2-2 composite sandwich with 2 layers of carbon fiber, 2 layers of fiberglass, and 2 layers of carbon fiber again, which we also make in-house, as both stages are the same diameter. We use an external coupler made of carbon fiber to hold both stages together on ascent. On the booster, we also have 2 exhaust holes to vent out a lot of the hot gas that comes from the ignition of the second stage as we are using hot staging. As we are using the forward retention method for each of the motors, we have a minimum diameter retainer here in each of the booster tubes. As we are surface mounting the fins, we also did 3 layers of tip-to-tip using fiberglass, using 2 layers, the same fiberglass that we do for our body tubes, and 1 layer, a thinner, more of a finishing fiberglass. This is to provide structural reinforcement on ascent and to provide structural reinforcement when the tube hits the ground. For motors, we chose a motor that has shorter burn time but higher thrust for booster in order to provide that quick punch to get off the ground. And for sustainer, we chose a motor that had a longer burn time but lower thrust to still maintain that above 2 thrust to weight ratio, but provide that longer burn time in order to go higher and maintain that speed.
Hey, I'm Trey Barberini. I'm the payload lead for the Argonia Cup competition this year. The main challenge of the Argonia Cup is to see how many golf balls you can get as high as possible. We have decided to use 10 golf balls. As you increase golf balls past 10, the reward significantly decreases per golf ball added. More golf balls means more weight, and the lighter a rocket, the higher we can make it go. There are 2 main parts of the payload. The first part is the electronics bracket. On this electronics bracket, we have a GPS and a magnetic switch. This is to make sure that we can track the position of the rocket whenever it lands. The next component of the payload is the golf ball sleeve. This sleeve holds all of the golf balls and sits in the nose cone and the payload tube of the rocket. This is the sleeve that we flew for our test flight, but since then we've decided to increase the number of golf balls by 1, so we have a slightly longer tube in the workings right now. For the assembly of the payload, the electronics bracket slides down into the nose cone, and then a singular golf ball is dropped on top. This golf ball is friction fit to the sides of the nose cone. Then, the golf ball sleeve is slid onto the nose cone and sits just on top. Finally, the rest of the payload tube is slid on top. The nose cone and the payload tube are then bolted in, and the entire payload is now complete.
Because the rocket is minimum diameter, we can't attach rail buttons to where the motor is. To solve this problem, we're using a flyaway rail guide. We used a very similar system last year, but this year we made some upgrades to the design and flew our first version on the test flight. This version worked great, but there's still much to improve. Part of what we want to do this year is not just learn from our own mistakes, but learn from mistakes that we've seen from others. And last year, one thing that led to a lot of teams being disqualified was a failure to track down the rocket. Because of this, we've decided to double up on the amount of GPSs in our rocket so that every component can be found even in a worst-case scenario. All in all, this will be a lot of firsts for Auburn engineering. We're hoping to break our previous altitude record, flying the first minimum diameter rocket in Auburn history, as well as the smallest diameter rocket the school's ever seen. A massive thank you to the Cloudbusters and good luck to the other teams. We'll see you in Argonia!